From the emails you send to the shows you stream, pretty much everything we do these days relies on the cloud. We just expect it to work, right? But that reliability, that constant onness, it's not magic. It's actually built on a promise, a kind of digital contract between you and the massive data centers that power our world.
So, what happens when that promise gets broken? When your favorite service goes down, who's actually responsible? Who's on the hook? It seems like a simple question, but the answer is surprisingly deep, and it all comes down to the rules of the game.
In this rule book, the thing that our trust in the cloud is really built on, it has a name. It's this sort of hidden contract that spells out the entire relationship between a cloud provider and us, the users. It's called a Service Level Agreement, or SLA for short. And this isn't just some friendly handshake or a vague promise. No, it's a formal, often legally binding contract. It's the document that transforms a casual service into a measurable, guaranteed commitment. So, what's actually inside one of these things? Well, an SLA is going to tell you exactly what percentage of the time a service is guaranteed to be up and running. It defines performance goals, and this is the important part, it lists the penalties the provider has to pay if they fail to meet those goals. But what you won't see is their secret sauce. They're not going to tell you exactly how their system is built or what specific encryption they use. The SLA doesn't really care how they keep their promise, just that they do. And really, the heart of that promise, it all comes down to the numbers. When a provider guarantees something like, say, 99.9% uptime, that sounds amazing, but you gotta understand what that number really means in the real world. Let's just take a number. How about this one, 99.5%? I mean, hey, if you got that score on a test, you'd be thrilled, right? That's a solid A. But in the world of cloud computing, what does a 99.5% success rate actually allow for? Okay, let's make this real. Imagine a cloud service guarantees it can handle 10,000 requests every single hour with 99.5% success. So the question is, how many of those requests are allowed to fail before the company is breaking its own contract? Any ideas? The answer is 50. 50 failed requests every single hour. All of a sudden, 99.5% doesn't sound quite so perfect anymore, does it? It's a very specific, very calculated margin for error. And what's so interesting is that the math here is actually super simple. You just take the total, 100%, subtract the success rate, and that gives you the acceptable failure rate. In this case, 0.5%. Then you just apply that to the total number of requests. The key thing to get here is that SLAs aren't just vague feelings. They are based on cold, hard, verifiable math. And that, right there, is why the SLA is the absolute foundation of our trust. It sets crystal clear, measurable expectations. But, this raises a much bigger question. How on earth do cloud providers build an engine, powerful and reliable enough to even make these kinds of promises to begin with? Well, it all starts with data. And I don't mean just a little bit of data. We are talking about truly unimaginable amounts of it. See, to handle information at a cloud scale, you can't just use the kind of database you might run on your laptop. You need something completely different. And the solution is this huge shift in how databases are designed. On the left, you've got a traditional database. It's built to run on one single, powerful server. But on the right, you see a parallel database. Its architecture is called shared nothing, which is just a way of saying it's a whole cluster of independent computers that don't share memory or disk space. This lets it split a single query across all of those machines at once. And that is the secret to doing analytics at cloud scale. Okay, so that's how you store and get to the data across thousands of machines. But how do you actually process all of it? For that, Google came up with this brilliant model that basically works like a giant digital assembly line. It's called MapReduce. And at its heart, it's really just a recipe, a programming framework for chewing through a massive computational problem by breaking it into lots of tiny independent tasks that can all be run at the same time across a whole army of computers. The whole process kicks off with the map phase. So imagine you've got a mountain of raw data. The map job is kind of like giving a small shovel to thousands of workers. Each one of those workers, or mappers, grabs their little chunk of data and does one simple thing. They sort it and they tag it, getting it ready for the next step. Next up is this really crucial and honestly often overlooked phase called shuffle and sort. This is the logistical brain of the whole operation. Its job is to gather all of that tag data from all the thousands of mappers and group all the related items together. Now, because it's handling so much data at once, this is a really common place for things to get stuck. If this part fails, let's say it runs out of disk space, the entire job just grinds to a halt. And finally, we get to the reduce phase. Now that everything is all neatly grouped and sorted, a new set of workers, we call them reducers, can come in and do the final calculation. So one reducer might get all the data that was tagged Apple and just count it up, while another gets all the data tagged orange and finds the total. And boom, that's how you get your final answer. But, and this is a big but, MapReduce isn't a silver bullet. It is fantastic for these huge one-and-done jobs like indexing the entire internet. But it's actually really inefficient for tasks that need to loop over the same data again and again, like a lot of machine learning algorithms. And why is that? Well, because after every single pass, it has to write all of its work back down to disk, and then read it all back up again for the next loop. That constant reloading is just a huge bottleneck. So we've got the parallel databases to hold the data, and we've got MapReduce to process it. But what's the thing that manages the actual physical hardware? You know, the thousands of servers, the networking gear, the storage arrays, the whole shebang. Well, you need an operating system for the entire data center. And that's exactly where a platform like OpenStack comes into the picture. You can think of it as the master controller for the cloud. It's the OS that gives administrators a single pane of glass to manage these massive pools of resources and lets you, the user, spin up virtual machines and storage whenever you need them. Now, OpenStack enables a practice that, at first glance, sounds completely impossible. Let's say a physical server has 100 virtual CPUs, or vCPUs. Is it possible for a cloud provider to actually promise more than 100 vCPUs to its customers from that one single machine? And the answer, amazingly, is yes. This is where the economics of the cloud get really fascinating. Using something called an overcommit ratio, in this case 1.5 to 1, a provider can take a machine that physically has 100 CPU cores and promise a total of 150 cores to its customers. It feels like breaking the laws of physics, but it's actually a very calculated risk. This whole idea is called overcommitment, and it's basically the economic engine that makes the cloud profitable. It's a calculated bet that all of those different customers aren't going to try and use 100% of their promised computing power at the exact same moment. You know, it's the exact same principle airlines use when they overbook flights. They're just betting that a few people won't show up. So when you pull it all together, the cloud is this incredible marvel of engineering. It's built on these mathematical promises called SLAs, it's powered by a massive data processing engine, and it's all balanced on a really clever economic bet. But as our society weaves these services deeper and deeper into everything we do, you have to stop and ask a final question. Is a promise of good enough really going to be good enough for the future we're all building?